Hi, my name is Haiti Garcia, and this is my video presentation for Lab 4 on oscillations for Intro to Physics at Georgia Tech. So today we're gonna start with a quick introduction to the lab and what we're doing, and we're gonna cover the observational model, which we put onto the tracker software, and then the computational model, which we computed through Python code. Then we're gonna compare the models and end with a conclusion. So in today's lab, we're going to be observing the motion of an oscillating object that's being swung with a spring. We're also going to model the same experiment through code and then compare our data. So a couple of important physics ideas and things that we need to keep in mind before we jump into the lab. First is Newton's second law, which says that the net force equals change in momentum divided by change in time. And then we have our update formulas, so that's the velocity and position update formulas. Also, since this lab does have oscillations, then we need to take into account simple harmonic motion, which is given by time equals 2 pi times the square root of m divided by k, m being the mass of the object that's being swung and k being the stiffness of the spring. Some important forces for this lab are the force of gravity and the force of the spring, and then the energy principle, including kinetic and gravitational energies. Another thing we need to keep in mind before we cover the experiment, is that the system is in this lab is going to be the Earth, spring, and the mass, and this is the vector of our initial position. So I started off by using the video and applying it through Tracker. After we track the motion of the object at the bottom of the spring, you can see we get sine and cosine graphs for position versus time graphs in the x and y directions. After this, I was able to solve for k by using the given mass and finding the time by getting the total time of 3 wavelengths and dividing it by 3, and then I was able to insert those two data to the simple harmonic motion formula and then solve for k. And then for L naught, we just used the net force, which is mg equals ks, and I got 1.451 meters. As for a computational model, I started by updating the mass and the initial position, and then I also went ahead and put in the two values that we just solved for, which would be the spring constant and the initial relaxed length of the spring. And then I also edited the energies, so that would be the kinetic and the gravitational and the spring potential force. Energies. Next, I went ahead and plugged in the gravity force, the spring force, and the net force, and as well as the update formulas. And then after that, we just went ahead and calculated all of the energies as well as the change in energy. So for our results, we were able to conclude that it does follow the energy principle, because as you can see in the final graph, delta E stays at a constant 0 throughout the entirety of the experiment. So now we can answer the final questions. Is the energy principle satisfied? Yes, because in our resulting graph, the orange line representing the energy principle stays relatively at a constant 0 throughout the oscillation. Now, comparing the two estimates about the periods of oscillations for each of the graphs, I would say that the x position versus time graph would be longer, because there is less effect in the x direction due to the forces than there is for the y direction. And finally, I do want to cover some potential sources of error that could have happened throughout this lab. For example, we didn't account for other forces like drag force and other forces of friction that might have been in the spring, and we only considered one type of energy. We didn't really consider any rotational or any thermal energy. And then also there could have been human error in applying the video to the tracker software.